Welcome to Durham and welcome to the Department of Computer Science. Today I would like to give you an impression of what it is like to study the MSc in Scientific Computing and Data Analysis, or MiSCADA for short, here in Durham. I'm Dr. Anne Reinartz. I'm the director of MiSCADA. MiSCADA is a course made by scientists for the next generation of scientists. Our courses focus on building an understanding of the algorithms and software tools that have become ubiquitous in modern science. The course instruction is structured into two parts. Every student takes MiSCADA's methods training, where you learn how to write large-scale scientific simulations and how to analyze large quantities of very complex data. But methods shouldn't remain abstract, so each MiSCADA student has a specialization area, a domain to which these core skills are applied. The specializations we currently offer are financial technology, earth and environmental sciences, astrophysics, and computer vision and robotics. The components every student takes in Term 1 are scientific computing, high-performance computing, introductory statistics and machine learning, and professional skills. In Term 2, students have a choice of optional modules, such as Advanced Statistical and Machine Learning, Foundations and Unsupervised Learning, Advanced Statistics and Machine Learning, Regression and Classification, Performance Modeling, Vectorization and GPU Programming, Data Acquisition and Image Processing, Advanced Algorithms and Discrete Systems, and Computational Linear Algebra and Continuous Systems. As you can see, not all optional modules are available to all streams. Finally, in Term 3, you will have the opportunity to work closely with an academic on a research project, which will form your dissertation. For now, let's have a look at what your core lectures might look like. In particular, let's take a look at high-performance computing with Dr. Christopher Marcotte.
Hello everyone, my name is Chris Marcotte, and today I'll introduce you to some of the concepts you'll see with me in Introduction to High Performance Computing as one of the core modules in the MiSCADA program. We're only going to discuss two topics today: who needs parallel computing and Flynn's taxonomy. Our aim for this taster session is for you to understand the growing ubiquity and need for parallel computing and to understand some of the organizing axes for parallel hardware. Let's begin with our first question. Who needs parallel computing? And to answer this question, we are going to look at the development of microprocessors over the last 50 years. This dataset is managed by Carl Rupp and collaborators and covers the period from 1970 to 2024. I want to draw your attention to the 5 properties plotted in this figure: the number of transistors, the frequency of the microprocessor, the typical power draw, the number of logical cores, and what we all cared about 10 years ago, the single-threaded performance. Since 2005, the number of transistors in a microprocessor has continued to increase. Indeed, this is an exponential trend that you may have heard of, called Moore's Law, after the founder of Intel. The typical power has plateaued, while the frequency has decreased slightly. The first important thing to note is that the single-threaded performance is plateauing. New cores are not doubling or tripling their predecessor's performance anymore. We're now thrilled if a new core is faster at all. The second important thing to note is that the number of cores in a microprocessor has been increasing steadily for the last 20 years. This means that if we want software to run more quickly than it did before, we need to learn to exploit parallel computing, even in the low-performance computing of consumer hardware. But this is not a module about low-performance computing, it's about high-performance computing. If we have a look at the performance of the top 500 supercomputers since the 1990s, we'll see that performance is increasing exponentially, though the exponent of increase has become smaller in the last 10 years or so. What this is measuring is the throughput of a distributed linear algebra calculation, how much progress is made per unit time by all the nodes in the supercomputer working collaboratively. That is, at the high end, it is the performance of multiple machines working together that matters. Now, lest you leave this session thinking bigger is always better, or all we need is scale, the number of processors is not the only contribution to performance. We're also trying to solve ever larger problems, whether that be due to increased fidelity or scale. Over the time span, from the mid-1950s to the mid-1970s, algorithmic improvements for linear solvers went from banded Gaussian elimination to full multi-grid approaches and accounted for a reduction in the cost by more than the improvement due to Moore's law or due to hardware alone. One way to interpret this is that without algorithmic improvements, we would still be solving problems we struggled with in the 1980s. All of this is to say, you need parallel computing. Even if you never write software for a supercomputer for the rest of your career, you will still be doing some meaningful computing, and you will need to account for the increasing parallelism of the hardware and assess the appropriateness of your algorithms for your problem. So given that you need parallel computing, how might we think about computing hardware which includes your efficient smartphone all the way up to the largest distributed clusters? Flynn, in 1966, described a simple taxonomy of computing hardware organized around the number of data streams and the number of instruction streams being ingested by the CPU. Let's briefly discuss the main categories. We organize these configurations into 4 categories so that when we speak of single instruction and single data, or SISD, we are referring to the canonical model of a computer which executes a single instruction on a single piece of data at a time. But we can also have that single instruction act on multiple pieces of data. This is SIMD. You may have heard this called vectorization. More exotic configurations are also possible. With multiple instruction single data, we are describing a machine with redundancy that executes multiple instructions on a single piece of data at a time. The most general configuration is the one we'll consider through the bulk of high-performance computing module: multiple instruction and multiple data. This is a machine which executes multiple instructions on multiple pieces of data simultaneously and involves some form of communication, either in memory or through explicit messaging. This is all quite abstract, so let's consider a short example. In this program, we declare an array and write the results of a very expensive function call to the elements of that array. If we stare at this code for a bit, we should notice that the calculation of AI and the calculation of AJ are independent for j not equal to I. So we can speed this up by exploiting multiple execution units. In this example, we have modified the loop increment to increase by p, the number of processors we can devote to this task, and offsetting the index of A by the thread index TID. For thread indices between 0 and p-1, then those p processors reduce the computation time proportional to p. On a desktop, this might be a factor of 8 or 16, while on a cluster this could be a factor of thousands. Finally, I want to leave you with some further reading. These references include the datasets, figures, and concepts used in this taster lecture for Introduction to High-Performance Computing. I hope to see you in Core 1B.